Good morning. Welcome to this session about the introduction to OpenMP for GPUs. So in case you were not here yesterday and maybe swapped sessions in one way or another, this morning we're going to focus on GPUs the same way yesterday we focused on CPUs, and we're going to build on what you have already seen to see what we can do with GPUs this time and try to use these beasts of computational power, even if you have even more later to play with. Anyway, so as always, first the individuals from whom I inspire this content, and then the acknowledgement of the tools I use and the license, which in case you were not here yesterday or you forgot, it means that you can use these slides more or less in any way you want, unless you want to modify those slides and make it look like I endorsed the changes you've put in them, which is not the case. So these slides, like yesterday, are designed for live presentation. They have very few notes, as you may have seen yesterday, because I fill the blanks with my speaking. So feel free to take notes, of course. Exactly like yesterday, the moment of truth. So please, logging on Bridges, try to get a new repository, clone it, and the idea will be the same thing, trying to compile the first exercise so that if something goes wrong, it goes wrong now. So we can help you fix it, and then we're good to go together, okay? The slides are on the Moodle, so you can download the slides directly. It can be easier, rather than copy-pasting this, if you have the slides directly, to just click on the link, this repository, that will take you to the GitHub directly. Tell me if one link is dead or incorrect or something. Is there anyone who still cannot access Bridges at all? Perfect. Okay, in case you see that you cannot compile because it says MVC doesn't exist or something, it's because you need that line here. So what I did was I put that line in my bashrc, which is the file that is loaded every time you log in. So in my case, it was loaded automatically. That's why I didn't spot it. But you have that line in the submission script file. So submit_bridges, you can find this file in every folder. It will be what the script we will use to run the GPU programs on the GPU nodes on Bridges. So you can either copy-paste it from the file or just type it from there. If you want, put it in your bashrc so that every time you log in on Bridges, it automatically loads it for you. Makes your life easy if you want. And you want to look again? Yeah. Wait, yes. You have this in the file, but did you type it in the console? You need to type that in the console, because what happens is this script, when you're going to send your jobs to the GPU nodes on Bridges, it will load everything on the GPU nodes if needed, but we are on the login nodes. We're compiling on the login nodes, so that's why on the login nodes they're not loaded yet. And actually, we don't even need to. Yeah, let's compile locally. It's easier to compile locally. Because this, by default, compiles directly on the GPU nodes, but it's easier if you compile locally. It's more interactive. So if you find a mistake when you're a beginner, it's way more intuitive. Has anyone managed to get it to work? Okay, that's going well. Yes. Oh, to connect on Bridges? You cannot clone the repo. Okay. Yes, you're going to see that if you try to run your code directly, so I'm in the first exercise folder, and I have compiled it. You can see the preamble in green. That's my binary. If I try to run it, it says there are 0 GPUs. And the reason is there are 0 GPUs on the login node. So yesterday, it was fine to run your programs on the login nodes because they were taking 3 seconds at most. So it can be accepted. tolerated. But in this case, for GPU programs, you will have to use the compute nodes, no longer the login nodes. So this is a quick check for you to know if you're running on the login nodes or the GPU compute nodes. We even have a reservation for the duration of this session, which is right here, which is this line here, okay? Why? Because GPU nodes may be very popular at that time, so maybe there will be many jobs submitted. So to make your life easier, we have taken an entire node and reserved it just for you for this session, okay? The same way, you have nodes, 2 full GPU nodes that have been reserved for you for the programming challenge after the end of every day. So for example, on Wednesday, the summer school finishes at 4 that day. So from 4 onwards, if you want to work on the programming challenge, you have these 2 reserved GPU nodes for you. You have all the reservation names. The way it works is you just have a reservation name to put in your script to say, oh, I would like to submit to GPU nodes, please, the 2 that have been reserved for me. And the name for today, for this session, is this one in this line, okay? You can also, I checked this morning, you can submit without the reservation. It seemed that it was not very busy and my job ran right away. But if you want to make your life easier, use the reservation. Good for everybody? We can get going? Yes, 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 yes. Yeah, you have the one from last year, I believe. That's the Bridges script from last year. It's like HPCSS something. That's the one from last year. The one from this year is OMP GPU 1 Joule 9. So you will have to put that in all your scripts. And you'll have to make sure there's no space between the hashtag and sbatch, otherwise it just becomes a normal comment. I've turned that into a normal comment by default so that when the reservation name stops being active, you're no longer stopped in your submission script. Because if you ask for a reservation that no longer exists, the job manager says, no, I'm sorry, I cannot run your job because that thing doesn't exist. So instead, it just runs it on the normal GPU reservation. Okay, I think we've had enough. All good for this? We get started with the actual stuff? Let's do it. So today we're going to see a few topics like yesterday. We're going to start right away with how do we actually, how we're going to offload, it's called offloading, how we're going to transfer the execution of your program to the GPU, okay? First, to make sure that we all know what we're talking about, what are GPUs? What does that GPU acronym stand for? Yes, graphics processing unit. Why? Because originally these devices were designed to process graphics. Yeah, I know, I'm not bringing you something really outstanding right here. Because the architectures are really different from the one in CPUs. So don't think that GPUs are just beefy CPUs and that's it. They are totally different devices which have totally different characteristics to abide by if you want performance. So today, I'm going to show you correctness, like yesterday. First, how to transfer your program to a GPU. Then once this is done correctly and your program is valid, then we can focus on the fun stuff and optimize everything in between. Okay? So I'm taking a quick example here to show you the difference between a CPU and a GPU. Let's say that we're developing our own little Photoshop software, and we have a picture, and we would like to make every pixel in that picture 20% darker, okay? So here is my super fancy picture, high resolution, as you can tell. With a CPU, the way it would work is you take every pixel in turn and you make it darker, okay? With a GPU, the way it works is you're going to work on entire subsections at once. I'm simplifying a few things here and there here for the example, but that's an introduction, so we can afford this kind of simplifications. And once you have the entire subsection, you make this entire subsection darker at once. So you can process the picture entire subsections at a time. So it's much faster. I have an example from the Mythbusters. Maybe you know them? Let's say, maybe you know the video already even? Where they explain the difference between the CPU and the GPU.
I introduced to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up. Ladies and gentlemen,
Leonardo 2.0.
When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10, 9,
8,
7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
So that's how GPUs work. My favorite part in this video remains the person's laughter at the end. When everything works, it's ha, ha, ha. That's my favorite part. I just love that. Anyway, so yes, it was this video. So you've seen that GPUs have this army of what seems to be, in this case, little pipes that can throw only one little colored ball, but they can all do it at the same time. So if you have a look on bridges, I hope that my information is still up to date. On bridges, the nodes we have, I think, are V100. So if you look at the core, at the clock of the core, the clock frequency, it's 1.3 gigahertz with a boost at 1.5. I can bet more or less all your laptops have cores that have a much higher clock frequency than this. So you may be thinking, why are we even using that thing here? It's like a weak core. Yes, it's actually a weak core. But you have 5,000 of them in each GPU. I don't think your laptop has 5,000 cores. Well, you have a much better laptop than me. You have quite some bandwidth on the GPU, right? So if you want to move data inside the GPU, once the data is inside the GPU, yeah, you can move it fast. For those of you who want to get some thermal design, then what happens is 5,000 cores per GPU. Every GPU node on bridges has 8 GPUs. So that's 40,000 GPU cores. That's a lot. And that's one node. So the advantages of GPUs is that, number one, they're just computational tanks, okay? Especially compared to CPUs. Yeah, there's even worse than GPUs, but GPUs already compared to CPUs is a big jump. They're more power efficient, and if we do a calculation on a per core basis of the price, you see that between the CPU, where it comes roughly to 270 per core, to a GPU, which is £1 per core, it's like, okay, so it's more powerful, it's more power efficient, it's cheaper. Why do we even bother using CPUs ever again? It's like, okay, you gave us introduction to OpenMP for CPUs yesterday, but after this, I'll never use CPUs ever again. You may want to reconsider this. Why? Because GPUs also have limitations. Number one, memory transfers. But you just said that we have 900 gigabytes a second of bandwidth. Yes, once the data is on the GPU already. But first, that data has to move from where your CPU is to that GPU, and that's not 900 gigabytes a second. And we have latency as well. Bandwidth is one thing, latency is another one. There's something called divergence. Divergence is when you have an if statement in your code, when you have branches, that's called divergence. An example of divergence. What happens is GPUs have this very interesting, simple ISA where, instruction set architecture, where the whole army, I'm going to simplify here, and I will go in a bit more detail at the end of this session, the whole army of cores that you have, these 5,000 cores, they can all do the same action at the very same time, just like you've seen in the video. Every pipeline was just throwing one ball of color, and that's it. They were just using a different color, but that's all they were doing. The issue is they all need to do the very same action. If it's the case, every time you do this, it's every 5,000 cores that can do an action. However, if two different actions are to be done, one, let's say, by the first half of the cores, and the other half by the other action by the other half of the cores, what happens is the program will say, okay, first I'm going to execute that statement. All the cores that needs to do it, you do it. All the cores that do not do this one but will do the second operation, you wait for now. So effectively, you have a massive army, but half of them is sleeping. So when you have a lot of divergence in your program, that's something that will degrade the performance of GPU programs. There are techniques to minimize it, or try to alleviate, yes, but that's one of the original limitations you will have now to deal with. Branches on CPUs, absolutely not a problem. CPUs have much more complex sets of instructions behind the scenes. They can handle branch prediction and all these things really well. That's my favorite, but it's maybe a bit technical, talking about the coalescing of memory accesses. However, nevertheless, even if, of course, GPUs are not perfect, they are still doing something really well, which is why they've been around for a long time now, and they're not going away anytime soon. So what happened is, initially, they were meant only for graphical processing, but what happened one day is someone started to think, what happened if we try to kind of hijack the way they work so we could use all that power for more or less any arbitrary program, my computational chemistry program on my astrophysics simulation? And that's where GPU came in, and it became what's called general processing GPU, because you use a graphics device for something that is not graphics. So effectively, you've generalized that device. If you want to do this, one very popular approach to do it is CUDA, developed by NVIDIA. One reason that I argue CUDA has become so popular is because when I discovered GPU programming in 2013, where it barely started, I think, NVIDIA was the one that had developed an amazing documentation. So every time you wanted to learn something and it was CUDA, you had wonderful pages with examples and descriptions and analysis and form messages and everything. In other words, whatever it is you're working on for your research, if you want your users, or if you want to spread it at some point, you need to make your users able to learn everything about it very nicely, easily, conveniently. Don't think it's something just for research. That's called friction. It's used a lot in commercial environments. You've seen when you want to join something or pay for a product, the form is always lovely. A form with a single button, the UI is amazing, reactivity is awesome, you have the customer support right available for you. Do you have any question, anything? And when you want to leave that same company, all of a sudden you can't find the link. It's lost in like 15 pages of terms and conditions. Yeah, but it was a Friday at 4 p.m., it's closed at 3 p.m. 55, I'm sorry, try again. That's friction. It's made on purpose. OpenACC was another solution to program GPUs, and what we used to use in the International HPC Summer School until 2 years ago. What happened 2 years ago is the support from NVIDIA of OpenMP on NVIDIA GPUs has become much better, to the point that now OpenMP is a viable option. So we thought, since we're already teaching OpenMP for CPUs, if we teach OpenMP for GPUs as well, now you just have to know OpenMP well, and you can even combine, because of course, what we've learned on CPUs, we're going to reapply it on GPUs. So now you just have to learn OpenMP and you're good to go with all CPUs, all GPUs. So let's try to see how that actually works behind the scenes. I'm going to use two terms here. Number one is the host. The host is where your program begins execution, okay? Roughly, quickly said, your CPUs, okay? And the target is the device to which you would like to transfer the execution of your program. In our case, GPUs. Why don't you just say GPUs then? Because your device can be something else, FPGAs and all the fancy things that hardware people will come up with over the years, okay? Exactly like yesterday, we're going to see constructs, parallel, critical, barrier, all these things. The first one we're going to see here is the target construct. Why? Because that's the one that actually transfers execution to your GPUs. We're going to explain later the sequential and synchronous aspect of that transfer, because at the very end of this session, we'll see how to do it asynchronously to start overlapping things around. But that's optimizing performance, first, correctness. So, in theory, you can more or less combine everything with OpenMP constructs. In practice, there's a smaller number of constructs we use it with. So let's take an example. Every time, C and Fortran, again, just like yesterday. If I want to transfer the execution of block B, okay, just the block B on the GPU, all I need to do is to wrap this into a target construct. Okay? Yes, it's really 3 words, and now you're already on the GPU. Thank you, OpenMP. So outside of the target, you're on the host, so CPUs. So anything you run before and after the target, CPUs. Inside the target, GPUs. Simple, right? Now you may wonder, yes, okay, when I run my program, I know exactly where I stand at first. But when I'm inside a function or something, how can I know if I'm currently on the GPU or the CPU? Maybe the code that calls my function now is executed on the GPU and I cannot know. We have a function for this, simple function, OMP is initial device. And that will tell you if you're currently on the host or not. Simple check. How to use it? Just put that in an if statement and that's it. If it returns the value equivalent to true, it means you're the host, otherwise you're on one of the target devices. Make sense? Yes. Yes. In this case, it won't block it that much. Why? How to reply without spoiling what comes next? Okay, I'm going to find a very sneaky answer, but technically absolutely correct, so that I don't have to give you the right answer just yet. Technically, everybody on the GPU is going to have the very same solution here. Everybody on the GPU will all say, we're on the GPU. So nobody is saying, oh, no, I'm not on the GPU, and wait for the other to do the other branch. That worked. Okay, well then I've talked enough. So time for you to try to offload a code execution to the GPU. Remember something. If you try to run your program locally, you have no GPUs available. So if inside your target construct, you call the OMP as initial device, and he says, nope, I'm not on the GPU, and you're like, you're just inside the target construct. It's because you have no GPUs available. remember to copy this code from the first exercise to the other submission script. Is there anyone using Fortran? Yes. Did it work when you tried to compile? A syntax error. Okay, that's something else. No? Okay. If I try to compile it right away. Oh, yeah, okay, that's different. Get an error message? So if we have, and I think, oh yes, we do. To the Bridges 2 experts in the room, we will need your services, because it seems we have a little issue somewhere. Okay, let's declare this. Mine doesn't complain. Oh, that's the hello world, by the way. Preamble, it says something else. Okay, interesting. So then I'll have a look at the preamble. Thank you, because you helped me spot a mistake in the preamble then. Well, no, the error message I was looking for was an error message that another student had about a compiler runtime function that was not compatible, something like this. Oh, so if you try to compile on the compute nodes, it doesn't work. Okay. Okay, so Fortran, just for Fortran programmers, not for C. Also for C? Okay. Oh, well, so then it's not a Fortran thing. So we need to compile on the login nodes. Got it. Okay, where are we up to? Who managed to get it done? Yes. Did you check you were actually on the GPU? Yes, and for those who did you get the, yeah, I'm running on the GPU? Yeah, no, I've had at the same time some students doing, and some doing, Make sure you do not run your program locally. You need to make sure you execute through the submission script. Okay, so sbatch, let me show you the command in case you're not used to this. Sbatch submission. Bad point for you, Ludovic. On Fortran, you just have the submit.slurm, so you don't even have to bother about anything. You just have one script. On the C, submit bridges. Okay. Yes. Let's try to proceed and see what you've done. So the first part was to offload that loop to the GPU, okay? So how did you do it? There was a good start. I heard pragma something. Yes. Okay. Shift all this. Okay. How do I know if I'm on the GPU or not? How can I tell? What's the function I need to call? Yes. Exactly. Okay, let's try to compile this. It's happy. Let's try to run it. Equally happy. Well, at least for the submission part. I didn't update the name of the reservation. So if you submit with this reservation name, it's going to say, I'm sorry, I cannot run it because this reservation no longer exists. This one expired last year. So you need a new reservation. Where can you find it? Just in the script number 1. So you go in the C folder, and then you have the submission script here for bridges. That's where you have it. Okay? Okay, so now it's executed. Let's print the output. I'm on the CPU. Oh, tough luck. Let's see what we did. Can someone help me spot what the problem is? So it seems exactly. Yeah, if it's the initial device, it means a CPU. If it's not the initial device, it means probably a GPU. In our case, only GPU is available, so yes. So let's compile. Let's execute. An easy way to find all your jobs is -- me. And it shows only your jobs, but in this case, they're already finished. I'm on the GPU. Good. And then we have everything here. Fine. Okay? So you have already run now your first program on the GPU, and it took you 3 OpenMP words, including 2 for the Sentinel. That's a good ratio of effort to result. Yes? It's the host, yes. Yes. The initial device is the host. The target devices are the GPUs and everything else. It's a bit of a confusing terminology, I agree. Oh, bye-bye, Mona Lisa. Okay, so exactly like yesterday, when we had threads, the first thing we started to do was, okay, how do we pass data to these threads? Shared, private, first private. It's going to be the same thing here. Now we have the GPU. What we're going to want to do is send the data to the GPU. So we're going to see what's called data mapping. Again, it's really the same as when we were on the CPU yesterday and we had parallel, and then we were using shared with default none to make my teacher proud, remember? On the GPU, we're going to have something a bit equivalent. So by default, what happens? Because something happened by default, just like yesterday. If you would not use shared, it would be shared by default. On GPU, it's a bit trickier. Here we have a classic scalar, an integer, and then we have an array. By default, the integer is passed as a kind of first private, and the array is passed as shared. Why did I say yesterday to always explicitly pass your variables? It's because this scalar that is now mapped at first private used to be mapped in a different way in OpenMP 4.0, which was before the OpenMP 5.0 that we're now using. So do not rely on implicit behaviors. Always tell exactly how you want it when you pass your variables, okay? Statically allocated arrays are passed as a to from. I'm going to explain what that is in a second. You can see it as somehow shared, but that's really simplifying, so I'm going to explain to from, don't worry. And here I explain how it works with the scalar by default, but since we don't use by default now, we don't really need this. Okay, so what happens is, implicitly if you pass arrays, you have your array on the host, okay, that has 2 values, 10 and 20. When you transfer the execution, when you offload execution to your GPU, that array is going to be passed, okay? The modifications you're going to do are going to be reflected on that array that is currently on the GPU, and you will bring the final value of this array back to the host and overwrite the array that was on the host, okay? You can see it kind of shared. It's like what you passed is what I will be modifying. I will be modifying this one. Since the GPU and the CPU, to simplify and be a bit outdated, do not share memory directly. Now they can, but leave that on the side for now. They will have a mirror if you want. So the GPU will have a local copy of that array, but it will override the array when it will send all the data back from the GPU. Okay, the host will just receive the array and overwrite its own array with your values. That's what happens implicitly. With scalars, integers, what happens implicitly is you declare your integer, you initialize it. When you're going to offload the execution to the GPU, your modifications will not change that red version, which will be the one that will be returned and maybe overwriting the original blue variable. It will be put in a local copy on the side, on the GPU. So you will have your own copy on the GPU. So it means that the red variable that you're going to return has never changed. So anything you've done with this integer never changed. So don't rely on implicit movements. That's really the rule. By contrast, we can map everything explicitly, which is what we're going to learn right now, with a map clause. It's the clauses just like yesterday. Yesterday we've seen reduction clauses, we've seen schedule clauses. Same thing here. It's going to bring additional information about how we want something done. So we're going to see three. These three can be used just with the map clause there, okay? Pragma, OMP, target, map, and then the map type, so one of these three, and your variables. Okay? A bit like shared private first private. Really works more or less the same way. And the equivalent in, no, not equivalent in Fortran. We have the Fortran here already, sorry. Alloc and delete, we're going to see these two after, because they are for more performance reasons, typically. So let's start with to from. It's probably the most intuitive. The value that the data had before you called the transfer to the OpenMP to the GPU will be sent to the device, okay, to the target device. And the final value that this variable on the GPU has at the very end is going to be brought back to the host. Okay, so that's the classic case of, okay, here's a variable, do something with it, send it back to me, and I have my updated variable at the end. Classic. Okay? Now, sometimes we don't need the value back. Okay? Sometimes we just need like, okay, here's some value because it's maybe a read-only. You're never going to update these variables, so don't even bother giving back to me. Why would we like to not even get the variable back? Because we save the data transfer. Remember, data transfers to and from the GPU very slow. So if we can afford not to bring the data back, that's good news. So if it's a read-only variable, just keep it. It's fine. I'm going to send it to you. Keep it. So the value at the start is the one that the variable you give had. That's good. But well, you'll never bring it back. So how to do it? Simple. OMP target map to, and then your variables. Same thing. If you want to change variables, you put little commas, and that's it. Done. So we've seen to from. We've seen to. Guess what comes next? From. From is the opposite, where you're not going to send any value, so it will be uninitialized, but you're definitely getting the value at the very end. So you may be wondering, why would we ever need this for? Think of a local, maybe a local reduction or calculating a total of something on the GPU. The original value is going to be useless because the GPU can initialize your total to 0 itself. It can do it itself. You don't need to send 0. It can do it itself. It's going to calculate everything, and then it's going to tell you at the end, oh, the result is 52. Okay? So we can save half of the data transfers again. Make sense? Yes? Okay. To do it, you know now, just from, and you're good to go. Now, with arrays, there's something slightly different from yesterday. Yesterday, whether you were sending an integer or an array, you were just saying shared my array and was done. When you're going to program on GPUs, you now have something new in the equation, which is you're going to tell what portion of the array you want to send. So the notation here can be confusing, so let's take 2 seconds really to read it well. I'm going to send my array A. The first element I'm going to send is the one at index 0, okay, before the colon. And I am going to send 10 elements, the number after the colons. So it's not index of the first and index of the last. It's index of the first and how many elements, okay? It's a simple one, but it's very easy to get wrong. Why would you like to, oh yeah, you also have that in the slides, just to be sure. Why would you even want to have that? Like, well, by default, I just want to pass the full array. No, because you may want to work on sub-arrays. You may not need the entire array. So if you can save a lot of data transfers, that's already good news. And even better, at the end of this session, we're going to see how to use multiple GPUs as well. We have 8 GPUs, no reason not to use them all. So if you have a massive, massive array, you may start to send some portions to some GPUs and start to use everything concurrently. Because at the end of this session, from yesterday, you already know how to use all the CPUs on the core, all the CPUs on a node. So you can use all the cores inside all the CPUs. So if you have 256 cores like on bridges, you know now how to use all 256 cores. Now you'll know how to use on top of this all 8 GPUs. And if you have done MPI before, or if you take the slides from the other session, you will also learn how to use all the nodes. So you'll be able to use all the nodes, and inside each node, all the CPUs and all the GPUs. Basically, you can now use anything you want, more or less. Using it efficiently may require a few more sessions, but now you'll be able to use everything. So another example here. Yes, that's a new one that was added from last time. I ran this workshop a week ago in an HPC summer school that I created in the UK. It's one of the students said, oh, how does it work when we have like different mappings? Do we put like 2 and then comma from? And I said, no, actually, if it's different mappings, it's different map clauses, okay? It's a minor thing, but in case you were wondering, say thank you to that student. That's another example of feedback. This one is 1 week old, okay? So that's thanks to the feedback from last week. So your feedback may be implemented tonight. Well, enough of me talking. Time for you to have fun. So target construct, and this time you'll handle the data movements. Yes? It doesn't have to be at compiler time. So it doesn't have to be at compiler time, but there will not be checks. So if you tell OpenMP, if you have an array of 2 elements, and you say, I'm going to send 10 elements, it will be, sure, you're going to have a seg fault, but it will try. So, yeah, classic C behavior.